Hello again.
Hello.
How's
How,
it going?
how are you? What's going on?
It's all going over all good over here. How about
That's
yourself?
pretty cool, pretty good. I feel pretty good today, feel pretty confident, I guess.
Excellent. Well,
Yeah,
confidence is
yeah.
very important in statistics, isn't it?
It is. And it's very important for this video too, isn't it?
Absolutely.
Specifically. So I'm confident about this video.
Indeed. Well, can
Uh,
I start this video with a story?
Sure, of course. You're showing a bunch of confidence right now by starting off the video, right, with the story.
Absolutely. Well, uh, once upon a time, about 100 years ago, there lived a British man called Ronald Fisher, and he worked at an agricultural research station, and his job was to help food production.
All right.
But one day during his job, he was making a cup of tea for one of his coworkers,
Okay.
and he poured the milk first in this cup of tea.
Oh, wait a
Now,
minute.
yeah,
There's a debate whether milk first or tea first.
indeed, yes,
Oh, okay. Wow. This is controversial, so.
absolutely. And I can't remember the name of the woman, the female researcher, but she refused to drink this tea because he poured the milk first.
All right.
And he was saying, like, no, there's no difference. It doesn't matter if it's milk first or tea first. It doesn't matter if you add a cold thing to a hot thing or a hot thing to a cold thing. And she said, oh no, I can tell. I can always tell. So he decided to do an experiment. And he was going to make 8 cups of tea, 4 of them milk first, 4 of them water first.
All right.
And she got every single one correct. She
Well
could
done.
tell, absolutely. Because it wasn't known at the time
Okay.
that if you add a cold thing to a hot thing, the proteins, well, the cold milk, the proteins in the milk,
Uh-huh.
they get scalded and they turn a little bit caramelly.
All
And
right.
that's the taste that she
Okay.
liked.
Uh-huh.
And being a man of science, Fisher thought to himself, well, she's got every single one right. But what if I got one of the orders wrong? Like, what if she didn't get them all right? Like, at what point do I need to decide that she's right or not? Well, it would have been better because I only made 8 cups of tea. It would have been better if I made 12.
Yes, that's right. That's right. Kick up the number. There's more information there, isn't there?
Absolutely.
All right.
And then it was another researcher, it was a Polish American researcher, and I have his name here, uh, Jerzy Neyman. I'm probably
Okay.
not pronouncing that very well, so I'm very sorry. He took that idea and he created what we call the confidence interval.
Really? Okay. All right.
Indeed. And that's what we're going to be talking about today, isn't
That's
it?
brilliant, right? That's so cool, eh? From that particular instance, whether it was tea first or milk first, right?
Hmm.
So the proper way to get the caramel is the milk first, then the tea.
It's tea first, add the milk to the
Tea,
tea.
add the milk to the tea. Okay, okay, all right. I remember there's a rule too. I remember while I was going through chemistry, it was add acid to water just like you oughter. So
Amazing.
that makes a difference too. So that was kind of going through my mind. So, all right, tea, then milk.
Hmm.
Got it. All right, excellent. So maybe we should talk a little bit about those confidence intervals that were created
Absolutely.
for that and see some other applications for it too, right?
Yes,
I see right behind you, you're prepared because you've
absolutely.
got, it looks like a confidence interval on a mean,
Absolutely. Yep.
and as well as a confidence interval on a proportion.
Absolutely.
Very
Yes.
cool, very
Very
cool.
similar equations, but used quite differently.
Yeah. There's information like on the top one when we're looking at the top one, we see that we have a standard deviation and we have a square root of the sample size, right?
Hmm.
So that gives us a sense of the standard error. Okay.
Yes.
So we're taking the z value, right? The z value we get according to how confident we want to be, right? If we're following a particular distribution, namely the normal distribution, we're
Yeah.
looking at z values, right?
Hmm.
So that's going to let us know how far out we need to go to capture whatever confidence level we're looking for, right? So
Absolutely.
95% confidence interval, we better make sure we're looking at the middle 95% of that normal distribution, right?
Mm.
If we wanted a little bit, a 90% confidence interval, we'd come in a little bit, I imagine, right?
Yes.
I'm going to see if I can, my drawing skills are, if they're still with me here. So I need to, oh, whiteboard. Here we go. Hopefully.
I love the whiteboard.
Okay. Yeah, if it's working correctly and if the internet connection holds up. So remember, I'm in this cave over here. So
Oh,
the Wi-Fi sometimes is a little bit, shoddy. And you got the bats interfering with all the whatever
oh,
high frequency stuff up there.
dreadful. It's anomalies like that that reduce our confidence, isn't it?
Yes, it does. It does. But we're gonna build it back up, right? We're gonna. Oh, it's error. We try. Oh my God. Oh, here it goes. All right, there it goes. It needed just to warm up a little bit. All right. So can we see it? Can we see the whiteboard?
Can do.
All right, great. All right, so we've got some kind of a huge sample space here. So that's all the values, our whole population. We take a certain sample in here, right? Okay.
Nice.
So we want to find possibly some kind of a mean that's represented in the whole population, but we've got instead a sample mean that comes
Hmm.
from a sample of n with a certain standard deviation, say s, since the sample standard deviation, right? And there's also some standard deviation that's involved with the population as well, right? Okay.
Mm.
I think I'm using all these symbols correctly, right?
I think so.
And let's throw in the capital N here for however many is in our population. It's not the nicest handwriting, but hopefully
Same.
throw some color in here in a little bit, I'm sure.
Sure.
Okay, so we want to find out where mu is, right? We want to know where the mean is of the population, right?
Hmm.
So our best guess would be X bar, right? But according to how confident we want to be, if we know that there's an underlying, somewhat of a distribution, an underlying distribution that's somewhat normal, right?
Hmm.
We can use our normal distribution, right? And say, you know what? I've got some kind of a value that I'm going to find, but I want to set up a confidence interval that lets me know that if I go out and resample however many I sampled, however many I had in my sample, if I went and resampled, that I would end up containing the correct mean 95% of the time or 90% of the time.
Yes,
Okay.
absolutely.
And I think that's the way that we're supposed to interpret the confidence interval is that if I go out and resample the same amount, if I do it 100 times, 95% of the times I'll be capturing the true mean.
Absolutely.
As opposed to saying, here's one confidence interval I've gotten from this particular sample. I'm 95% sure that the mean is in there. That's not quite the correct interpretation, I believe. Okay.
Right.
All right, cool. All right,
Yeah.
just to get that that legal
Indeed.
disclaimer out of the way.
Yeah. Yeah, because you can never be like 100% sure of something,
Of
but
course,
being 95% sure, that's good enough.
not
Not in all
bad.
cases. If you're working in medicine and you're testing a new drug or a new vaccine, having a 95% confidence interval probably isn't appropriate because this is people's health you're talking about. Maybe you need a confidence interval of 99 or 99.9.
Right, right. That's exactly right. That's depending. So you kind of set
Mm.
up what you decide what your confidence interval needs to be, right?
Yes, absolutely.
If it's an advertising or something that's less, it's not going to huge impact other than monetary. Maybe you're willing to take an 80% confidence interval. Okay.
Hmm.
And as we want to get more and more and more confident, we're going to be looking at bigger and bigger and bigger bigger and bigger and bigger tolerance on each side of that of our estimator. In this
Mm.
particular case, X bar is giving us an estimate for mu, right? So we're trying to figure out now, basically, how confident we want to be by setting it to 95% if we want, or whatever other value we need to, right? Depending on what our, how confident we want to be. Right. Okay. So that's how we get our Z value. So I believe, let me see if I can get rid of some of this here. All right. Where's my eraser? Here we go. Some of this we'll leave, some we'll get rid of. Okay. So when we have a particular value, we're trying to find out what mu is, right? Our best guess is X bar, right? So we need to add these bits, right? Is that what we need to add?
We do.
Because it looks like we have X bar plus and minus, right? So the same bits on each side, our Z value, right, that we're interested in. And I'm going to throw it in as alpha over 2. The reason
Love
it's
that.
alpha over 2, because we'll see this notation quite a bit.
Mm.
Alpha, that represents our level of significance. So that's the amount of error we're giving ourselves, which corresponds to a confidence interval. I'm going to call that C for right now, of 95%, right?
Yes.
So that's the
So,
amount that we're allowing ourselves. Okay.
so our confidence is 1 minus the alpha.
Yes, that's exactly right. That's exactly right. There's 1 minus the significance. So if we're looking at the middle 95, the stuff that's out here, that's what represents our alpha. So if it's split into 2, that's where we're coming up with this bit right here. Okay. So in our particular case, if we want a 95% confidence interval, our Z alpha over 2 is going to be what, 0.025?
Yeah.
Yeah, so it's going to be 0.025. So we have to find these Z values, and I'll call them Z critical and negative Z critical or confidence or whatever. Z sub C. Okay. We have to find what those values are. Okay. Well, we're looking at the negative and the positive, right? But that's kind of handled with that plus or minus right there. Okay.
Yeah.
So let's figure it out. How are we going to figure it out? Probably by a table. Probably look at a table. Should we bring up a table, or should we assume that people know how to use a table?
I don't have a table prepared. I think we
Okay,
looked at a
well,
table in another.
I'll tell you what. Let's actually do this. I'm going to. Here's what I'll do. Let me stop this share real quick. If I can. Oops. Stop the share. What is it? Close whiteboard. There we go. All right, cool. So I'm going to pull up a standard normal table, right? Is that what we need?
Yes, because we're working with the normal distribution.
Standard normal. Should have had this up for us, huh? What do you think? Images?
No, I like how these videos diverge. Like, oh, we've got an idea,
Yeah,
let's talk about it.
sometimes I'm putting in, but I'm not showing everybody what I'm doing. So I'm putting in standard normal distribution table into a Google search, and I'm looking at images, and I found a nice one here. Let's see if we can pop it up here. And this is a nice one. This is a nice one. Okay. So now you get to see it. Here it is. Okay. Look at this one. Nice big fonts. Hopefully. Is it coming up?
Oh, there we go.
There we are. Okay, cool. Here's our normal distribution, and here is our density function, right? So our density function, which this kind of follows this particular term right here, and then it's an exponential function. It's not really showing it right here specifically. They're calling it phi, it looks like, right?
Cool.
But we're looking at the area under the curve, and that's what's being represented down here in this table. Okay? So if we want a value, a z value that's along here, that's what we're looking for. This in here is represented by the bits in the table. So I'm looking for a z value, which is going to be given along these, along this column right here, and along this row. Okay, so if I'm at 0.00, so that's what this is representing, 0.00. It means I'm exactly at 0. That means that the distribution, the area for under that curve is 50%, right? Is half of the distribution. So that's what this is telling me. If I want to have 50% of this distribution lying to the left of some z value, that z value better be 0.00, right? And as I move further this way, let me make that a little bigger. As I move further this way, the table's telling me all of this area. So I want to move this all the way up to where, somewhere, where the stuff behind it is how much?
That is a
If I-
0.025 value, isn't it?
0.025 is what's in the tail, right? But I
Right.
don't have that value here, right? That's somewhere over here, right?
Ah,
So I need to use the symmetry here to say to myself, you know what? If I'm trying to find where the line is that chops off the first 2.5%, I can also find that exact same value as a positive value on the other end, right?
excellent.
So that means I've got to come all the way out to what probability here in order that how much is behind me, right? If the middle is 95% and the stuff that's to the left of the middle is 2.5, then what's left for over here?
Ah, well, that's going to be 90, oh, hang on, 97.5%.
97.5% is exactly right. That's
Excellent.
right. That's right. Okay, so that's where we're going to find it on the other end. So we use the symmetry here. That's why they're really only showing stuff that's on the positive side of z, or the positive values of z, right?
Right.
So when we go down to 0.97, where is it? Oh, there it is, right? Is that it?
Yeah.
Yeah, exactly that. So that's 1.9. And then I got to go up this way to see that it's at 1.6, right?
Nice.
So probably a lot of people watching this video, let me stop this share. Probably a lot of people that have that are watching this video may have remember 1.96 coming up quite a bit when they're looking at 95% confidence interval, right? And sometimes you'll see the number 2. That's kind of an estimation, right?
Yep.
2 standard deviations away, that's 95%. Cool. So we've got, let's go back here then. Where are we? Our whiteboard. Okay, so it's just a case of knowing what is your right? What is your best guess, right? And then we're going to add and subtract the tolerance, which is going to be our z value. In our case, when we were looking at what was it, 95%, we found 1.96 was the value that we needed, right? Okay. If we wanted to be more confident, that would have gone a little bit maybe past 2, right? So we would have to look up specifically what those z values would be. Right. So 1.96, And then, well, we need a sense of the distribution, right? To be able to say, to take this 1.96 that we've drawn from the standard normal to put on to multiply it basically by a sense of the distribution in that sample. And that's given by our standard deviation, whatever that happened to be, right?
Hmm.
Divided by the square root of however many in our sample, right?
Excellent.
Right. So what happens now if we have more and more, and if we go from 8 cups of tea to 12 cups of tea, what happens?
The um I want to say the probability, but maybe the penchant for error is reduced.
Yes, yes,
Yeah.
that's right. We're able to tighten up those confidence intervals, that confidence tolerance.
Hmm.
Say, you know what, we got more information. We still have that same estimate, but we're still 95% confident, but now within this particular value or within this particular tolerance, right?
Mm,
That makes sense?
absolutely.
Awesome, awesome. So yeah, so that's how we would do it for a sample or for a population mean.
Mm,
How we would go about doing it for population mean. But also what's kind of cool is that second equation that you have up there, right?
yes.
So let's look at that one because that looks like a confidence interval. Let me see if I can let me get rid of this stuff. Okay. Oh, that's not the way to get rid of it.
Oh, scribble it all out.
There, okay, never mind this. How do you? I'll figure it out at some point, Laura. Have faith in me. I'll figure it out.
I have every confidence
Thank
interval in
you.
you.
Thank you. That is just that makes my confidence boost now. So we've got okay. So we could go out and ask a question now, and we can say, yeah, whatever question we're asking, there's a yes or no response.
Sure.
Okay. So if let's say we ask n people, right? And X amount of them say answer yes to the question. So maybe do you like ice cream? Okay.
Mm,
So we go out and ask 100 people, and let's say 70 of them say yes, that they like them, right? That they like ice cream. Uh,
my kind of people.
Right. So, and I've actually put out like in some of the stats classes that I present, uh, just to get some to get some engagement and to get some information. I'll ask the specific question: do you like ice cream or not? And then we're able to set up confidence intervals to figure out we have a sample. What proportion of the world likes ice cream? And then we make major decisions after that. After that piece of information. So, all right. So we may have a idea of what, or we have sorry, we have a sample proportion that we're able to figure out. So
Yeah,
how many people like ice cream over however many people we asked, right?
sure.
So we may want to make some kind of an inference on what the actual population proportion, sorry, what the actual proportion of the population that likes ice cream. So we're trying to find out where this particular proportion is, right?
Hmm.
That makes sense?
Yes, it's not
So
p hat this time. It's
it's,
just p.
it's just P. So P is the analogous, I guess, to mu.
Mm,
P is talking about the whole population, the population proportion. Here's our sample. This is where we're going to get P hat from, right?
nice.
That makes sense? Okay, so we're asking, like we were asking, where's mu? And we said, here's X bar, and here's where this confident that it's within here and here, right? Here
Hmm.
we're asking what proportion of the population answers yes to this question or likes ice cream, as an example. And we're going to end up that specific amount, we're going to be able to estimate from our sample. Okay?
Sure.
So we say that, and you may even see it in this particular notation. We can say that P our actual population proportion is between p hat minus the stuff that's behind you right now that I can't see,
Oh, yeah.
and p hat, opa, plus that. Oh, there it is. Cool. Thank you. Square root. Wait a minute. What am I doing here?
Oh,
Square. Oh, no, no, no. Here, let me write it down here. Wait a minute. Oh, sorry. So it's
it's
p
fine.
hat. I'm gonna write it the way they have it. P hat plus and minus z star. Yeah, that's cool. Square root of p hat times 1 minus p hat. Okay. So the probability that they say yes times the probability they say no,
Mm-hmm.
right? Also divided by n. Okay.
Yes.
Yes. All right. So I was kind of trying to go with you see what I was trying to do there,
Yeah.
right? So this would have been this amount here, this bit here, or all of this bit, oops, along with the z is what I was going to put here and here. Okay.
Mm-hmm.
All right, cool. All right, good enough.
So I have a question for you now.
Yes, go ahead.
So would the Z statistic, let's say we're still working in 95% confidence, would the Z statistic for proportion still be 1.96?
That's a great question. That's a great question because we don't know that we have something that's normally distributed here. That's an excellent question. That's an excellent question. We don't even know if we can use a normal distribution. So the rules that I've seen that I don't know where to cite to say where I've seen them, but
Mhm.
I remember, and people can check me on this, that if you have n times p hat and n times 1 minus p hat, if both of these simultaneously are greater than the number 5, then your distribution is close enough to normal because it is a binomial distribution, right?
Mhm.
Okay, so it's just making sure that it's not skewed too much towards the 0 or the 1 way or the other. So this is kind of the rule that I've seen. So even put a little bit in plainer language. You have to have at least 5 yeses and 5 nos,
Right.
basically. Yeah.
So that kind of is in agreement with the central limit theorem then, with like the greater the sample size, the more you can assume that it's normally distributed.
Yes, 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 yes. This particular sample, if we resampled.
Yeah.
So yeah, absolutely. So as it's making sure that we've got something that kind of looks normally distributed. Okay.
Excellent.
So meeting those conditions, we use exactly the same z value, right? Because
Hmm.
we're still looking for the middle 95%. So we'd be using the same z values. So
Excellent.
this right here. So as an example, should we yeah, if I said, let's say 70. All right, so let's do it for 70.
Hmm.
Let's do 2 examples. And if you have a pen or a calculator handy, that would be awesome.
I will get one up
All right, cool, cool, cool. That
on my
way
laptop
you
and
don't
I'll
have
put
to
it over
do
here.
anything.
There we go.
All right, here we go. So, all right, so that let's say as an example now, we've got on X, let's say 7 people out of 10 said yes, and we want a 95% confidence interval, which means we want a level of significance of 5%. Okay.
Hmm.
So we know that our Z value, right, is going to be 1.96.
Okay.
Wait a minute. Did I make a mistake here?
Oh,
I did, didn't I? I made a mistake here. How many yeses and how many nos do I have?
you have 7 yeses. Would it be 3 no's?
Yeah, so I can't use the normal distribution here.
Oh,
That's right. So
ah,
let's do this. Let's make this 15 then. How's that? Let's
right.
make this, okay? Oh my God, almost made a huge blunder there. If I make it 13, if I make it 13, it should be okay, right? I'll make it
Okay.
13. So that's 6 yeses and 7 nos, right? Yes, okay. Right, so let's see. So what's P hat? That's going to be 7 over 13, which you're going to help me with right now.
I am. Oh, 0.538.
538. So that's our value. That is our best guess,
Right.
right? Point, what do we say, 538?
Mm-hmm.
38. I gotta learn to write more legibly. All right, so there's that bit. So now we need to figure out this amount here that we're gonna add and subtract, okay?
Right.
So let's say, so that becomes equal to the 1.96 times the quantity, 0.538 times 1 minus that, which is what? 4 times 0.4. God, my writing is terrible. Point, getting a little bit upset with myself here. Okay, try that one more time. Times 0.538 multiplied by points, was it 462, I think.
Mhm.
Close that, divided by the 13. Okay. Sorry, I gave you so many nasty numbers there.
Okay. So I'm only using a basic calculator, I'm
Oh,
afraid.
oh, that's okay. And that's all raised to the 1/2. Okay.
Oh, yes. I
Get rid of that.
hang on. I forgot to square root it. Let
That's
me
okay.
divide it now by 1.96, and then I will um square root that, and then I will times that by 1.96. Okay, so it's going to be p hat, which is 0.538,
Uh-huh.
plus minus 0.271.
271. Okay, all right. That sounds about right to me. That sounds
Okay,
about right. It's pretty widespread, right?
yeah.
It's basically this is up to like what? 7.7 something or other. And this guy's down to 0.18 or something.
Yeah, I think so.
Yeah, so that, okay, is not surprising that that would be the tolerance because that's pretty small. It's a pretty small sample, isn't it?
Hmm.
Right? So what would happen if we had the same proportion, which would be what? If I tacked on 2 zeros there, it'd still be the same proportion. But now, whatever value you have, that 0.271, that would, I think, what would happen here?
Ah, well, we'd be dividing it by 130, but then square rooting all of that.
Right. But the proportions on top would be the same, right?
Hmm.
Okay, so those would be the same. We just would have 130, so we'd be dividing by 10, right?
Hmm.
But then we're taking the square root of that, so we're really dividing by the square root of 10.
Right.
So take that number, 0.271, and divide it by the square root of 10, and let's see how much tighter that gets.
Oh, hang on.
Sure, no problem.
Um, I've done the whole thing divided by the square root of 10, which has given us 3.16, which doesn't sound about right.
No, that doesn't sound right. Just take this number right here,
Okay.
right? As it is, and then
0.271.
and then divide that by square root of 10, right? Because 10 was what we divided by. It went from 130 or 13 to 130.
Oh, I cannot do this. Hang on.
That's okay. That's
0.271
okay. That's okay.
divided by.
I'll do it over here. No, that's not an issue, man. It's like it's when you're doing it on a regular calculator, it's the order of operations and you have to save a bunch of stuff. And yeah, it gets a little bit that's okay. I'm gonna do it right here.
That's right, I've got an answer.
Oh, do you? Go ahead. What's
Yeah.
that?
So to three significant figures or three decimal places, it's 0.09. No, it's not. 0.086. Sorry.
0.086. That's
Yes.
perfect. Awesome. So we see how much tighter we got because we had a lot more information, right?
Yeah.
So yeah, and probably this is one of the things that's used to be able to call an election if there's only two candidates, right?
hmm
So so yeah, it's pretty cool. It's pretty useful, right?
Absolutely.
Well done. I think that was pretty good, man.
Yeah, that
And
was a
it,
lot of fun.
and I'm gonna have some tea. Let me stop this here. And I'm gonna go have some tea and make sure is the milk warm? No, the milk is cold.
Milk's cold.
The
Yes.
milk's cold. Okay. The milk's cold. And it's the tea and then the milk in there. Perfect.
Yes. Scientifically proven.
Scientifically proven with the sample of 8, right?
Yes.
All right. Well, Laura, thank you so much. These videos are always so nice and really put me in a good mood. You know what I
Oh,
mean?
good. I'm very pleased.
And this one really boosted my confidence
Excellent.
just to get that terrible joke in one last time. All right, so I'll talk to you later, okay?
Lovely. All right.
Bye.